Welcome to the next lecture of module regression, and in this lecture we are talking about support vector machine. So what exactly support vector machine is and how it works and all the maths behind it you will be learning in this lecture. So what are the steps involved in support vector machine? Basically, a support vector machine can be used both as a classification model and a regression model. And in this particular lecture we are talking about how we'll be using this as a regression module. Okay, so the steps involved is, first of all, you get a training data set as obvious. Then we plot a data to a high dimensional space. I'll tell you what I'm saying, don't worry about that. Then we have to evaluate a kernel. Then we find the best hyperplane, and then the target is, when we are using support vector, the basic target or the first aim of support vector machine is to plot a non-linearly separable data to a high dimensional space and then make it a linear separable. After making that linear separable data, we plot a hyperplane in that. It is more or less similar to linear regression, but the thing is, here we can deal with a high dimensional data or a non-linearly separable data. Okay, in case of linear regression we are bound to work on a linear data set only, but in case of a support vector machine we can work on a non-linear data with much ease. I'll explain all these things. Okay, the understanding of kernel and hyperplane is very important when we are talking about support vector machine, and in the next coming lectures I'll be explaining you in detail that how kernel is useful and what hyperplane is. Okay, so don't worry about it, just go with the flow and understand what I'm saying. So what is the working of this model? So suppose this is our data set. Now we can draw this line or this plane or this regression line. Using this line we can separate our data linearly, right? So we can separate this data and this data in a linear fashion. That what linearly separable means. So it is linearly separable. Okay, and now I'll give you example of a non-linearly separable data. So suppose this is our data. Okay, and this is the data points of some different class. Okay, let's say that's our data, or yes. Okay, so now to separate these two data sets, what we have to do is we have to draw this hyperplane, right? But this is clearly not a linear separation of the data sets. So for that we need some kernel or we need some different model. We cannot solve this data set with the help of a linear regression model, right? So for that we need a because this data is a non-linearly separable data, so we have to use a different approach to work on this data. So first approach to work on a non-linearly separable data is to convert a data to a high dimensional space. What I mean to say is, suppose we have a one-dimensional data, okay, and these are my data points. Okay, and this one, and this one. So how I can separate the crosses? This data is from one class and the dotted data belonging to a different class. How I can separate this data in a linear fashion? So it is not possible here to do so. Why? Because if I make this line, then what is happening is these dots are still over here, and if I use this plane, then also I can't separate my data. Okay, but there is an approach to do this. For that, let me show you an example. If I use a scare function, okay, suppose a function in the form of x scare, and I plot these data points using this function. So what can I do is, I'll be having of this kind of function, right? This is a x scare function, let's say, and these are my data points. And if I plot, suppose that's my x value, right? And this will be my y value, y equals to f of x raised to the power of 2. So this is my x and this is my y. So what I am doing is I have increased the dimension of my data. How? If I plot this x value using this function, right? So what I'm saying that, say this value is a, b, c, d, e, f, g, h, I. Okay. So I am plotting a, b, c, d, e, f, g, h, I. All these values I am plotting. Okay. So what I mean to say is, so corresponding to this training point, I have value over here. Then corresponding to this, I have value over here, then here. And then for DEF, I am having values over here. And for GHI, I am having values over here, right? So I have increased the dimension of my data and I have plotted my data from a low dimensional space to a high dimensional space using a mathematical function, right? And now if you ask me that whether this data is a linearly separable data, then I'll say that yes. If I use this particular line, then yes, I have separated my this was basically cross data. Okay, so you can clearly see that we have separated our data in a linear fashion, right? And this has made our task so much easy. So this is one approach to deal with our data, right? What I'm doing is I am separating a non-linearly separable data which I can't solve using a linear regression or a basic model. What I am doing is I am converting that data to a high dimensional space so as to make it linearly separable, and then I can apply my approach. I can apply, or I can find out the hyperplane from for my data. Okay, so the linear regression line you were saying in a linear regression model, it's basically a hyperplane, and there is a way to plot a hyperplane also, which I'll be explaining you in the next coming lectures. Don't worry about that. Okay, so this is the basic step of support vector machine. What it does is it gets a training data, it increases the dimension of our data. This is one approach to increase the dimension of data. But the problem is, if we are doing these plotation functions, that I am converting the data and passing on the values to fx here and then plotting and then finding the hyperplane, in that case what is happening is I am making my model complex. I am increasing the computation of my model. So for that, the best approach to use is the kernel approach. So that's why we have to use kernels. Don't worry about that. I'll explain what kernel is in the next coming lecture. Okay, so this is how support vector works. It get trains over a data and then predict the result even over a non-linear separable data, but in an efficient manner. Okay, a better approach to solve this tech problem is the use of kernels. So what is a kernel? Kernel is a method of using a linear classifier to solve a non-linear problem. What it does is it converts a non-linear data or a linearly inseparable data to a linearly separable forms. What it does is basically it maps your original data into a high dimension space and makes it linear. But what it does is it doesn't change the dimensions of your data, it's just the mapping over it. Okay, so let's understand with the help of an example. You can clearly see that we are given a data set where we have these two columns, say x1 and x2, right? And these are data set. And now you can see that to differentiate our data, what we need to have is we need to have a non-linearly separable hypothesis, right? But our target is to have a linearly separable data so that we can put up a hyperplane in that. So what it does is we use a mapping function. Okay, so a mapping function is used as our kernel, right? So what we are doing is we are using a kernel, and here we have used a Gaussian kernel. Okay, so using a Gaussian kernel, when we put up a Gaussian kernel in this space, what it does is you can say it like that. These, if you'll see this data from a 2D scale, let's say you are seeing this data from this, it will give you a view like this, right? And when you're using a Gaussian surface, what is happening is these points are coming down and these points are just raising up. Okay, and now what we are doing is we are using a decision hyperplane, which is a hyperplane. Okay, so this decision surface is known as a hyperplane. So you can see that this hyperplane is basically what we are doing is we are linearly separating our data, right? So this plane is a linear plane, right? And this hypothesis was a non-linear hypothesis, right? So this is how a kernel is used in support vector machine. It basically maps your data in such a form that we can use a linearly separable hypothesis so as to classify or to predict your data. Okay, and now we'll see what a hyperplane is. As I have told you, when we have mapped our data using a kernel, then we use a hyperplane which separates, or I can say which can linearly separate our data. And this hyperplane is designed in such a way that, suppose if you are having a data class this, okay, or this, so this hyperplane will adjust itself. Suppose these are the extreme points of your data class, right? So this hypothesis, what it will do is your hyperplane will adjust itself according to these two extreme points. How? Suppose this is a point, this is a point, and your hyperplane will adjust itself in such a way that it gets equidistant from both these points, right? So what point it considers? It considers the extreme points of your data class. Okay, it picks up the data point which is the extreme of your data cluster or data class and place itself in such a way that it is equidistant from these extreme points. Okay, so it takes up the boundary condition and put itself just between it. Okay, and one more thing to notice is that this hyperplane is always having one dimension less than the ambient space. In the previous case of kernel, you have seen that we were plotting a kernel in a three-dimensional space. Okay, and your okay, so this was a three-dimensional space and your kernel is a two-dimensional decision surface. So this what I'm saying, this is what I'm saying, that your hyperplane is one dimension less than that of the ambient space. Okay, there are different type of kernels which we can use while training a machine learning model, but the more or easy, very prominent ones are a Gaussian surface. So this is how a Gaussian surface looks like that I have taken into the example. Then a sigmoid kernel. Okay, your Gaussian kernel looks like this. Okay, then the sigmoid one. So sigmoid one looks like this. Okay, where this is -1, this is 1, this is 0, and this is 0.5. Okay, so you can set these ranges according to yourself, but this is more or less a sigmoid function. If it is a negative value, then it will give it a 0. Okay, or if I set this like that. Okay, so this is how a sigmoid function is, right? So this is how a sigmoid is being plotted. You can see that it is a function like this, and similarly a function like this is being given over here. Then a polynomial function, it looks like this. You can say that a polynomial function that you are having, it's like this over here. Okay, it can also be of the shape like this, right? So these are the basic kernels that we use in general practice while training our machine learning models. Okay, as I have explained you in the intuition video how support vector works, in this particular lecture we'll be doing a hands-on code using support vector regression, and we'll see how it works and how it gives us a better result. Okay, so far we have studied linear regression and polynomial regression. where the linear regression was the most basic one and polynomial regression was an advanced version of linear regression. And support vector is somewhat different to both these approaches. Okay, so let's begin with our lecture. I have imported the libraries. These are the libraries that we'll be using in this particular code. So pandas, numpy, matplotlib are the basic ones, and then I have imported the model, that is support vector regressor. Then we have standard scaler to scale our data. We can also use a min-max scaler as per your choice. Then for splitting the data we have train test split, and then finally when the model predicts some value, to test the model we are calculating the mean squared error which we are importing from matrices module. Okay, so let's import our libraries. In the meantime, what we'll do is we'll import our data. So for the understanding of this particular algorithm, I am using the predefined data set inside the library, which is a Boston data set. So it is basically a housing data set where we have to predict the price of the houses based on given parameters. Let's import our data from sklearn dot datasets import Boston data. So load Boston. Okay, and then let's name the data as Boston data only. So Boston data equals to, this is same, load Boston. Okay, yeah, here we go. So now we have our Boston data with us. If I'll print this data for you, you can clearly see what it is. Okay, so that's basically the data we are given. These are the input values and these are the targeted parameters, and it's given the feature names as well. Okay, so let me show you what it exactly means. What are these features? So if we want any text, we can just use raw. Okay, so these are the features we are given in this data set, right? And these are the inference of these parameters. So CRIM means per capita crime rate by town. Similarly, ZN and all these features, all these parameters are required to predict the median value of owner occupied homes. That means what is the cost of that particular apartment in Boston. Okay, based on the parameters, that is the living condition, taxes, payments, persons living, average rooms, and all that. Okay, so now this data that we have loaded using load Boston, it's in array shape. So what we'll do is we'll convert these array to a data frame form so that we can easily apply our machine learning models over it. It will make our work a lot easier to do. Okay, so for that what we have to do is we'll simply use data frame. So data equals to pd dot data frame, right? And now what I'm gonna do is, first of all, I'll be using the data. This Boston data has two parts, data part and then target part. So first I'll take the data part and we'll create a data frame. Okay, for that what I'll do is I'll say Boston data, the loaded data we have. So Boston data dot data, and then the columns I want for the data frame. So columns equals to the same Boston data dot features. Okay, sorry, it's feature name. Okay, so it's nothing to worry about, or you don't need to mug up anything because you are already given over here. So all the features names are present in the feature name attribute, then the description in this attribute, and similarly the input are present corresponding to data attribute, and then all the output values, that is the median house values, are in the target. Okay, so we have used the data using dot data, then we have assigned the columns using dot features name. Okay, and if I'll wait a second, and if I'll print of this Boston data features, you can clearly see the features we have. Okay, so these are all these features till here, right, which are present in feature names. Okay, and this mid period is given to us separately in the form of targets, which will also combine, don't worry about it. So first of all, let's create the data. Okay, So data is ready now. Now we have to do is, let's see what data we have. So that's the input data we have with us. Okay. If you want to combine your data as you have been already doing, okay, for that what you need to do is you can simply say that you want to create another column. Okay, what is the name of that column? The name of that column is median value, as it is given over here. Okay, and then what you have to do is it's Boston data target. Okay, as simple as that. And now you have your complete data with you. So Boston data dot head. So you can see that we have the entire Boston housing data with us. These are all input parameters and this one is the output parameter, right? As simple as that. And now you can explore your data. So data dot info. So you have total of 506 entries in your data. That means this data has less entries in it. Okay, for training your machine learning model, you should consider the more the data you have, the better your models will train over it. Okay, but let's just understand how support vector works, how to use it. I have explained you how it works, but just let's see how you can use this support vector in a Python code to deal with whatever data you have. Okay, right. So let's also check the data description. So data dot describe, that's the basic stats you will have in your data. So if you'll see your medieval data, so that's the total count and the minimum value. So the minimum value is $5,000. Okay, because it's a convention, MEDV is given in $1,000. Okay, so it's $5,000 and the maximum of it is, so last one is the maximum, so maximum is $50,000. Okay, so that's the price range. So the data we have is a continuous data, it's not discrete. That's why we are applying a regression model over it, right? So now let's check whether we have a null value or not. I have already told you we don't have any null value, but in case if you want to check, what you have to do is you simply use data dot is null. Does your data has any null values? So is null, and then dot sum. If it has, then it will give you the sum of your data, the null values. Okay, so you can see in each column it's giving 0. That means there are no null values present in your data. As simple as that. And now it's time to split our data. Before feeding it to a machine learning model, we have to prepare the training and testing part. So for that, we'll prepare our training part. So we will prepare the input and the output values. Input you already know the target we have. The output is the target ones and rest of the features are the input. So we'll simply use data.drop because we have combined the data. So for that, we'll do drop the MEDV column because it's the targeted parameter we have, and drop the entire column, so mentioning the x is equals to 1. Then the output will be the removed column, that is the MEDV. So MEDV. Okay, so these are the input and output values we have. If I show you the input values we have, so you can see that we have all the input parameters with us and the MEDV will be present in the output, that is the targeted data frame. Okay, so we have our input and output data with us, and now you can see the input data we have is having different ranges. So it's in 0 to 1 and then it's so high, right? So we have to make our data, we have to scale our data so that it will not create any bias for a particular feature when we are training it using a machine learning model. So each parameter should have a equal say when we are dealing with the training of our models. It is our model which will decide which parameter is highly dependent, okay, or which parameter is important based on the variation or correlation with the output. But you have to feed in a data which is having the similar distributions, right? So for that, what we'll do is we'll scale our data. So for that, I have already imported the standard scaler over here. So I'll simply say scx equals to initializing the standard scalar we have, so standard scalar, and then the input will be scx dot fit transform the data. Okay, so here we go. If I'll show you the data now, you can see okay, yeah, so now this x is in the array form. Okay, so you can see that now we have our data in the range -1 to 1. Okay, so this is how standard scalar works. You might be thinking that we have changed the distribution or we have changed the data. No, we have kept the similar distribution. It's just like the values have been arranged as per the distribution. Okay, so the data is scaled now. Now what we have to do is we have to split our data, right? So for that I have already imported the train test split module. So we'll say xtrain comma xtest comma ytrain comma ytest, because it will return all the 4 components all together. So train test split, and then we have to pass on the input, the output, and the test size we have. So test size, let it be 0.2. okay, and random state you can mention as, let's say, 0. So here we go, data is pretty. Now let's check the shape of our data. So xtrain dot shape, right, 404 entries, xtest dot shape, ytrain dot shape, sorry. So we have 404 entries in the training part and 102 entries in the testing part. So moving on, using this data, let's train our model first. So we are working on a support vector regression module. So we have to import SVR, that is support vector regressor. So for that, let's name it as SVR equals to importing the SVR. Then we have to set the kernels. So let kernel be RBF over here. Okay, there are different kernels, the linear, polynomial. It's as per your choice. You have to see which kernels work, or moreover it's a hit and trial method. It's basically the hyperparameter selection. You train your models, or you take some of your data and train your model over that, keeping different combinations of the parameter, and whichever suits the best, you take in that parameter and train it over the entire data you have. So this is how it works. It's basically a somewhat of an intuition and a hit trial method. First of all, you look at your data and you realize that yes, this particular thing can work. Then you try different combinations and work it over. Then you see which works the best, and you take that hyperparameter into consideration and train your entire model over those parameters only. Okay, so it's SVR. So initializing the SVR, now what we have to do is we have to fit our data, right? So for training we have to do xtrain, then ytrain. Okay, so we are giving the training input and output. Okay, so our data is, our model is trained keeping these hyperparameter into consideration. We have just changed the kernel RBF and the random state value. Rest, these are the parameters. You can go into depth using the official documentation of scikit-learn. Okay, so now what we'll do is we'll predict the values. So for that we'll say, let's name it as ypredict or ypredict. Okay, and we'll say SVR dot predict. We have trained the model SVR and now we are predicting the X test values. So here we go, let's check the ypredict values. So you can see the ypredict values are like this, and if I just show you the ytest values we have, so these are the ytest values. Okay, so these are the ytest values. So for it's originally 22 and it's giving 25 over here. it was 50 and it's giving 19 over here. It was 23, it's giving 24 over here, right? So it was 21 almost and it's giving 21 almost over here. And you can see that these are the indexes, so the data is being randomly arranged using the train test split, right? And now we'll be comparing these values with the original y-test values, okay? And for that, what we are using mean squared error. So simply error equals to mean squared error, and then we'll pass on the values. So we'll compare the y predict with the original y test values. So it's y predict only, okay? So let's print the error. So we are getting a 40% error over here, okay? Don't worry about the results. The data we are using, it's not sufficient to train such a well-developed model, okay? The target was just to show you how you can use this model and how you can check your results. A 40% error means that if you are predicting a value, then this value is having 40% chances of being wrong and 60% chances of being right. You should target that this error be the least possible, okay? So the more data you will have, the more better you can train your models, okay? So this is how you perform all the stuff using the machine learning models. This is how you get a data set, prepare a data frame, then you pass on, you do the pre-processing steps, whatever required, then you split your data and then you feed it to your machine learning models. Your machine learning model select and trains over these data. For training your machine learning models, you have to choose the best hyperparameters possible. So these are the parameters we have in this model. Each parameter can have different options as well. So you can play with these options and see whichever suits the best, and then you can finally use that model to predict. And finally we predict our values, then we compare it using the mean squared error. We find the mean squared error because it's the continuous value, so a mean squared error will work perfectly fine over here. So that's how we check our model. So this was all for this lecture. I hope you would have understood how SVR works. So best of luck and keep following.